right. I will strive to get you to your coffee break with alacrity. So good morning. I want to talk to you about some new sketching approaches based on something called the set sketch. And I feel I need to start today with a couple of thank yous. First of all, because the vast majority of this work was done by a grad student, Daniel Baker, who's now gone into industry, and it wasn't convenient for him to be here today. The other person I should thank is Ottmar Ertl, who's a researcher at a place called Dynatrace in Austria, because the set sketch idea is his publication. So I'm going to strive today to sort of make sure I'm telling you when I'm telling you something that's an idea of Ottmar's from the set sketch paper versus when I'm telling you an improvement that's from our implementation in the Dashing 2 paper. So this talk is about sketching. We've heard a lot about sketching throughout the conference. The goal of sketching is to take enormous data sets, which might be sequencing data sets, and distill them down into extremely small data structures that can fit in relatively convenient layers of the memory hierarchy, but we can still ask questions about them later. So cardinality and similarity questions about them later. And the way this typically works is we take input sequencing data sets, we shred them into pieces, often into their constituent k-mers. And then every k-mer is sort of introduced to the sketch and has an opportunity to influence the value of the sketch. And some k-mers do, and some k-mers don't ultimately influence the value of the sketch. So to show it schematically, I want to talk about two separate approaches for sketching first. One is Minhash, very popular approach. So in Minhash, we start with our k-mers. We hash each individual k-mer with a hash function, sort of mix their bits all up like that. And then we get essentially a random value between 0 and, let's say, 2 to the 32 or 2 to the 64, depending on that hash function. So we get all these hash values, and then the way we pick the one that actually influences the sketch is we take the minimum. So we take the minimum of all the hash values, and that is installed in our sketch. Hyperlog is not so dissimilar. The main difference is the function that we use to decide how the hash values influence the sketch. In this case, we take the maximum of the leading zero count of the hash value. Leading zero count is just sort of how far to the right do we have to go before we see the first one among the most significant digits of the hash value. So both of these things function as what I'm going to call sort of a high watermark random variable, right? Either the max of the LZC or the negative of the min can be thought of as, if we're trying to, say, measure aggregate rainfall in this geographic area, it makes less sense for us to look down there and a lot more sense for us to look up here. We're measuring kind of over all the data, when did it hit its high water mark, and that is a useful quantity for estimating what we want to estimate. Okay, another way of viewing what we're doing, if we can remove the hash function for a moment, is that it's as though we're taking the input k-mers, using each of them, just take the bit representation of the k-mer and install it as the initial state into the random number generator, and we use a pseudo-random number generator to generate uniform random draws from 0 up to, let's say, 2 to the 32. That's another way to think of what we've been doing, and then we can take the exact same statistic. We can take the minimum from among those uniform random draws. This is essentially an equivalent way of thinking of Minhash. Similar with hyperlog, except maybe we replace that uniform random draw with a geometric random draw. So this is like a coin flip random variable. How many times do we flip a coin before we see the first heads? That mimics this process of counting how many leading zeros there are in the hash value. Okay, so to complete the sort of schematic picture here, we don't just do this once. You know, if we are using hash functions or if we're using random number generators, either way, we want to repeat this so that we have not just one high watermark random variable, but we have a whole collection of high watermark random variables in our sketch. And when they are concretized in our sketch like this, I'm going to often just call them registers, which is what they're called in the literature. So here's our array of M registers. Ultimately, our goals are to use the values of these registers to estimate things like cardinality and similarity. Cardinality of a single sketch or similarity between two sketches. So in the set sketch paper, Ertl argues for a sort of interesting new framework. He says, if we want composability of sketches, something we often want, in other words, we want to be able to combine two sketches and have essentially the sketch of the union of the two data sets. If we want idempotent updates, a nice thing to have. It's not strictly necessary, but it's a nice thing for sketches to have. And low relative error across orders of magnitude of cardinalities, not just up to some limit, then the high watermark random variable should have a certain form. And he argues it should have a form that's indicated on this slide here. I'm showing now something like the previous slides, except I've changed two things. I've changed the function in that red box so that now it says maximum of floor of negative log base b of, and now I've also changed the random draw strategy. The random draws are coming from an exponential distribution. Maybe not too shocking to see exponential since we saw geometric before. Exponential is the continuous memoryless random counterpart to the geometric. Okay, so now that we have this new form of high watermark random variable that looks like this, we have some questions, right, and maybe even some problems. So the first question that we might have is, what's going on with these variables a and b? So these variables a and b are essentially tuning parameters. They are used to make sure that the sketch is doing a good job across the actual dynamic range of data that we're trying to sketch. Multiple strategies for choosing A and B are in the two papers that I've already mentioned, the set sketch paper and our paper, the dashing 2 paper. I won't say much more about those. The other interesting things here, or perhaps even a dispiriting thing that we see when we look at this formula, is that every register ki is actually a function of all the input data, right? So all the input data can potentially affect any register value, which should make us a little bit pessimistic about the practicality of this approach, right? Usually we bend over backwards to avoid this. With Minhash, we use things like bottom k or one permutation. With hyperlog we use one permutation. Okay, so I want to spend a little time explaining why it's maybe not so bad, like why we don't necessarily expect in practice that will be a heavy-duty update procedure. And so the first thing I want to point out is that if we need to do a whole, notice that there's an exponential draw for every register and for every input item. If we'd like to generate a collection of exponential draws, let's say m exponential draws, one per register, we're helped by the fact that spacings between exponential draws, so between adjacent exponential draws, if I put them in order, are themselves exponentially distributed. So this actually helps us a little bit because we can write down a formula, this sort of recurring formula that says that one draw could be thought of as the previous draw plus a little bit, where the little bit comes from a new draw. Why would we do it this way? It seems a little indirect rather than just calling the random number generator m times. And the answer is we can generate new exponential a random draws by doing cumulative sums over the spacings, which gives them in increasing order. And that's going to give us an opportunity to do early stopping in a moment. So this actually comes with an opportunity of early stopping. It also comes with a problem, which is that if the exponential draws are in increasing order, we now need to sort of break the relationship between those increasing draws and the registers 1 through m. We don't want one register to always get large draws and another one to always get small draws. So to fix the problem, I will just very quickly state that we can, since we're already initializing a random number generator, we can do a Fisher-Yates shuffle to ensure that the registers that the draws are assigned to are random. So they're randomly shuffled. So the opportunity for early stopping comes from the fact that if we look again at the update rule, there's a maximum there, which means that our chance of updating k sub I is higher when that is big, and that is big when that, underlined in green, is small. So in other words, the smaller exponential draws are more likely to change the value of a register k sub I. And indeed, there are some draws that might be so big that they can't possibly influence any value of any register k sub I. Indeed, draws that are larger than the maximum of all the current register values can't possibly affect a register. And furthermore, no subsequent draws could possibly affect a register because they're in increasing order. So as soon as one of them fails to influence the sketch, the rest of them will also fail to influence the sketch. So here's a little simulation to demonstrate that. This is just showing 5 increasing exponential draws, one of which is below this maximum, the one at 1. But as soon as we reach that draw at 2, we're now above the maximum register value. That means that that will have no influence on the sketch, nor will any subsequent draw. So we can stop. And so this is wonderful. It solves the main problem that we had, because as the sketch fills, this maximum among all the register values will shrink, and this early stopping eventually, rather quickly, reaches a point where we get average, on average, constant time updates, despite the fact that all the input items are influencing all the registers. As a more practical matter, to make the rest of the equation relatively efficient and practical, we have to make computing logarithms fast. Right? We have a lot of logarithms to do here. One of them's obvious, and one of them's hidden inside the exponential draw. So let's start with the obvious one that's in blue here. So to deal with that, we actually just at update time, we don't log anything and don't truncate anything. We leave things in their raw form just as they come from the exponential draw. So in other words, we do this. So as we maintain our sketch during the additions, we're maintaining the minimum of all the exponential draws so far without any log or truncation. Only once we're finished with all the updates do we ultimately do the truncation, do the log. Now we have the final value for each register. So that gets rid of the vast majority of the logarithms we would have had to do. We only have to do m of them at the very end. The other trick, so now let me explain why there's a log hidden in the exponential draw, is because the exponential draws are done using inverse sampling, which is to say we like to do uniform draws. Those are easy. So in order to do an exponential draw, we do a uniform draw and then pump it through the inverse of the CDF for the exponential function that we're really trying to draw from. But once we do compute the inverse of the CDF of the exponential, we get a log. So there, that's where the final log is hiding there in the exponential A draw. We also need to address that because that's pretty computationally expensive. And so the way we do this is with fast approximate logs. This is actually a fairly well-known trick. They are not accurate, but for the version that I'm showing on the screen, it's known how far they're liable to be from the true value. And so if we know how far they're liable to be and we just assume the worst and assume that they're way, way, way too high according to that value, we can still sometimes see that even after we account for that, they're over our threshold, right? They're definitely over our threshold, even when we take this envelope of uncertainty into account, and we can stop anyway. And it's only when they perhaps are under our threshold that we need to compute the full fidelity logarithm and continue. Okay, so if I'm doing well, then I have time for two more major points about what the contributions are. So the first I want to say is that if your input data is if it's not reasonable to think of it in a flat way, as a flat set of items, if it's more reasonable to think of it as a multi-set, things that have associated multiplicities, or as a distribution even, then this particular formulation is particularly easy to adapt to that weighted setting. All we do is take the weights and multiply them into the rate parameter of the exponential draw. That's it. Right? So all the insights up until now still hold. If you want to adapt this method to a weighted setting, you simply multiply the weight in with the rate parameter for the exponential draws that you would do for that item. Okay, and that's essentially the Minhash method, also proposed by Ertl. I have a citation there. And so when you do this, your notion of the input data shifts. It's no longer a set. It's something more like a distribution. This means there's not really a notion of cardinality anymore, so there's no cardinality estimator. And further, the notion of similarity, the Jacquard similarity, also has to change. It changes into this thing called the probability Jacquard. This is a little not intuitive, and I can show you examples offline of why this sort of makes some sense. And it's a little simplified, what's on the slide. But that's the new notion of Jacquard that we would use in this setting. Okay, I said our goals were to estimate cardinalities and similarities, and that brings me to a final strength of this method, which is that the estimators for these two things are really quite simple in the set sketch formulation. So here's the estimator for cardinality. Everything here is completely straightforward. The only slightly complex thing is this register value histogram, the C sub k. So this is literally just if you take the values of all the registers in the sketch and you histogram them, that gets plugged into this formula. And that can be done at sketch building time, for example. So once you've built the sketch, you can build this histogram. You never have to build it again. You can also just estimate the cardinality. You never have to estimate it again. So that's a trick. That's a nice chunk of computation that you can do at the time you build an individual sketch. Then when it comes time to do something joint, where you're comparing two sketches, now let's look at the Jacquard similarity estimator that's shown here. The numerator is just two cardinalities added together. We just saw the cardinality estimator and said that that was simple. We have to now delve into what's the alpha and the beta in this equation, and here they are, and I'm going to tell you a little bit about them. But the main point is that they contain these things called D plus and D minus. D plus and D minus are just counts of the number of registers in A that are greater than or less than, for plus or minus, their counterparts in B, right? So this is the only joint statistic that has to be computed across the two sketches for the Jacquard estimator, which is amazing because this is very easy to compute. You can do it with, for example, vector instructions, right? So you can use SIMD instructions from the Intel instruction set and do chunks of these at a time, possibly even like 64 of these at a time. So this is a huge improvement over what was the state of the art for Jacquard similarity estimators from, for example, the hyperloglog paper, and this idea can actually be plugged directly back into the hyperloglog framework. So this same estimator can be used for hyperloglog. Okay, so now I've got a few results to show you. First, I want to show a series of experiments where we compared tools based on how well they were estimating Jacquard similarities. I've got the tools listed here. I've got the rough technique that they're using listed at the top. And this is over 1,000 pairs, over 1,000 genome pairs that were selected so as to cover a wide range of true Jacquard values. So some of these Jacquards are small and some of them are large that we're trying to estimate here. And in general, the set sketch has the lowest error. If you look at the rightmost two columns, most of the time, set sketch is doing the best. I didn't explain exactly what the HLL variant of set sketch was, but it's a little bit like if you took the set sketch and took 2 steps back, again, toward the hyperloglog. That's what it is. We also did experiments on ANI, which is average nucleotide identity, by taking our Jacquard estimates and putting them through the MASH distance formula, which gives you an ANI estimate, and compared different methods, sum of squared error, similarly to before. And here we find that actually the weighted version of the set sketch what had substantially lower error in estimating ANI, which is quite interesting. Also compared to dashing 1, the sketching time and in particular, the time required to do all pairs comparisons for the Jacquard similarity estimate are both much faster. The sketching time being faster probably due to early stopping, and the all pairs comparison time being simpler probably because of the simplicity of that Jacquard estimator. Set sketch can be considered a generalization of some of the prior approaches. So for example, if you set the B parameter, which is the log base, to 2, then what you have is something very similar in spirit to the hyperloglog. As B approaches 1 from above, you have something that approaches Minhash in spirit. But typical settings for B are probably going to be determined by practical considerations like how many bits you want your registers to fit into. And so two typical settings for B are shown here. Finally, to describe a few features of the software, part of the title of this talk and part of the title of the paper is about a larger sort of locality-sensitive hashing scheme that we put on top of this method to make it easier to do all pairs comparisons while rapidly filtering out comparisons that are liable to have low Jacquard similarity. I did not have time to talk about that today, so sorry, even though it's in the title. Dashing 2 can take DNA or protein inputs, including protein reduced alphabets, which can be helpful for more distant homology of proteins. It has support for inputs that are not necessarily fast A, fast Q. You can give it key weight pairs, and it'll operate in its weighted mode. You can give it bigwig files, leaf cutter files, and again, these are all sorts of inputs where it's natural to operate in a weighted mode. Those will all use the weighted mode of dashing 2. And it has support for estimating things other than just Jacquard and cardinality, like those shown there at the bottom. And so with that, let me point you to the software. It's at the GitHub link at the top. Let me thank again Daniel Baker and Otmar Erdl, and many thanks to our wonderful hosts here in Turkey, and thank you for listening.